Show it bigger, show it bigger, show it
There
bigger.
it is. It's called Stephan's Quintet.
Whoa. Oh my gosh.
Giovanna, what are we looking at?
Whoa.
Yes, so like it's a quintet.
Space nerds all over the internet are getting their minds blown by the new James Webb Space Telescope images coming out. This past week, there were 5 images plus 1 of Jupiter, just mind-blowing images, including this space nerd. My mind was blown as well. Last week, the first jaw-dropping images came out from the James Webb Space Telescope, humanity's new super system, $10 billion. The James Webb Space Telescope, 30 years in the making, launched Christmas present last Christmas 2021 and is just now coming online. The first images are literally mind-blowing. This first image from the primary sensors on the James Webb was a deep field image modeled after the famous Hubble telescope deep field study. This is the original Hubble telescope deep field study, and that was the furthest distance any human eyes had ever seen. That was in 1996, January, when this image came out. For those images, the giant Hubble Space Telescope stared at a rice grain-sized patch of dark sky for 10 days. Imagine that, 10 days. The Hubble image that emerged, this one, in January 1996, showed almost 3,000 galaxies. 3,000 galaxies in this dark, dark patch of sky. Think of that. Scientists were blown away. From the darkest point of the night sky, almost 3,000 galaxies, rice grain size, held at arm's length. Imagine that. Most of these little specks are large as our own Milky Way galaxy with hundreds of billions of stars. Now, 27 years later, our next generation telescope, the James Webb, has come online, and already it's generated a better image than the Hubble Deep Field in less than 12 hours. The original Hubble Deep Field took 10 days. 10 days. This is a clear image, a better image of that same rice grain sized patch of dark sky, except James Webb did it better in 1/20th of the time. Imagine that, 1/20th at the time. That is orders of magnitude better, and the detail is markedly increased. What will this mean? What will the James Webb Space Telescope mean for humanity? What breakthroughs can we hope to find? Well, let's speculate, why don't we? Why are these nerds losing their minds online? I have my own speculations, postulations. I'll show it in this video, so stick around.
Chris Lado, welcome to Lado Files.
I'm Chris Lado, a retired F-16 pilot. Now I make YouTube videos investigating unidentified aerial phenomena and the nature of the universe. These things are aligning between consciousness, our unknown, dark matter, our unknowns about the universe are all aligning and does seem to somehow relate. I also think it does relate to our misunderstanding of the universe and the cosmos. And I love seeing our paradigm shift, what I think is going on right now. This will be an exciting video. Stick around. If you do like this content, smash that like button right now. Subscribe to get notifications when I release videos. Normally on Friday, I try and release more than one a week. And if you want to support the channel, go to patreon.com/Chris Lado and join the team, get backstage access. Now on to the video. This was the original Hubble Deep Field image, released 1996 in January. You see here, each one of these little dots is a galaxy. Just so unbelievable. That took 10 days. So the shutter on the Hubble telescope was just open, staring at this piece of sky for 10 full days. Now, fast forward, now 27 years later, the next generation James Webb Space Telescope has come online, and it can look back. This was the first image they released, the poorly named SMACS 0723 image. I refer to it as the James Webb Deep Field. This first image looks back 13.1 billion years. And you can just imagine all the crazy stuff going on that we're going to find out about the universe just from this one image, right? You have a supercluster here, okay, and that's bending the light. Okay, so these are actually images of the same galaxy, okay, behind it. So it's actually acting as a lens, a gravitational lens. We have here, look at this thing. What is going on? Is this shooting out of this weird red galaxy shape? Here's some more bending going on around this super galaxy or galaxy cluster, whatever it is. I mean, look at this. Just right over here. This is a Milky Way sized galaxy. I mean, here's another one. It's a crazy shaped galaxy as well. There's some knife edges. Just amazing stuff going on from this image, which we'll find out so much more about it. NASA released these other images as well. This is the Carina Nebula. This beautiful photo, I think, shows the fine detail of what the James Webb Space Telescope can give us. It has multiple instruments, so the medium wave IR can see through this dust, okay, that the Hubble actually couldn't see through. So you actually see the stars forming in this nebula. The next one, Stephan's Quintet. This one is amazing. This galaxy is actually in the near ground, okay, not related, but these other galaxies here are being spiraled around a supermassive black hole. I mean, imagine that, a giant, massive, supermassive black hole is orbiting these galaxies. These galaxies are orbiting around this supermassive black hole. The Southern Ring Nebula is next. If you look, this shows actually the near wave IR of the James Webb. One of the instruments, the primary instrument, shows superfine detail, if you see in here. While the medium wave image can actually look through dust, so it actually can see at different frequencies, can look through dust, and now we can see inside that this is a binary system, and this one actually exploded. And that's what we're seeing is this explosion of gas and dust. It's just dust, or it's just random gas. Okay, it couldn't actually be ordered structure, right? But this highlights James Webb's ability to see through gas that we couldn't see before, to even see more of the universe that we weren't expecting. And then this was released. This shows that the atmosphere composition of WASP 96 Bravo. So this planet, exoplanet, can actually, James Webb can look through the light that's actually passing through the atmosphere and spectroanalyze it. So we can see that there is water, H2O at all these places. Okay, there is water on this planet. We can see it using the James Webb Space Telescope. This is just in the first week, everybody. One other image I'm excited about, I found this on the Discord actually, is this image that James Webb took of Jupiter. There were some questions on if James Webb could actually focus on objects in our solar system. This shows that it can, and it can get amazing photos right here. What you see here is the rings of Jupiter. Okay, we can see in these IR images is specific rings of Jupiter. We'll be able to see further into the gas, right? So you actually be to see further underneath the atmosphere of Jupiter. Wow, we're going to get so much information about our solar system, about the local area, about our galaxy, about other galaxies, the universe in general. It is amazing. So get ready for a marked increase in humanity's understanding of the cosmos. So what secrets will James Webb reveal for us about the universe? Let's speculate, shall we? I have a couple different ideas. Let's see what I think James Webb may reveal for us. What was your initial impression when you looked at the James Webb Deep Field image, the poorly named SMACS 0723? Personally, I thought it looked like microscopic images that we see of pond water. Antony van Leeuwenhoek, I call him Tony, his discovery and study of microscopic organisms in the 1600s, it was one of the most notable achievements of the golden age of Dutch exploration in the 1600s. Unfortunately, Leeuwenhoek never shared his lens construction techniques, which must have angered his contemporary Robert Hooke. The non-sharing Dutchman discovered protists, tiny multicellular organisms, and bacteria, small single-cell microorganisms. He also found the vacuole, little internal organelles of cells, inside cells, and the spermatozoa. That's actually the sperm cell. He found this using his new lens technology. This lens allowed him to see into a world he had never seen before. Imagine before 1623. Humanity had no idea of the scale and diversity of biological microbial life. The scientific world was in complete shock. In a single drop of pond water, not only was there life, there were thousands of tiny life forms, unimaginable amount of living organisms, structured matter, in size dimensions that we could only see when we had the right technology. Leeuwenhoek's new technology had created a paradigm shift in humanity's understanding of the universe and our place in it. So now we weren't the only dimension of organized life. If we look down in smaller dimensions, we also see life. Now, 400 years later, there are thousands of galaxies in a single dark point in the sky. Imagine that, thousands. If you hold a rice at arm's length, that is the Hubble and the James Webb Space Telescope Deep Field Image. Scientists today will not only be surprised by thousands of galaxies, each with billions of stars. Imagine each one of these little dots has hundreds of billions of stars with hundreds of billions of planets. Our scientists and us will continue to be surprised by the ordered structure of the cosmos that we're not expecting. When Tony Leeuwenhoek looked down at microscopic levels, they weren't expecting structured order, little things moving around, structured living order. It was the structured order that our laws didn't expect. That's what shocked scientists. Most likely, they just didn't believe the data. It took hundreds of years to actually believe it. So how can we have order where we humans are not, right? We're not there. We can't affect it. How could it be possible? And yet, this is what the new JWST images are showing us. In just these 5 images, we're seeing what looks like ordered matter. Why and how are galaxies orbiting around a black hole? Why and how are galaxies orbiting around a black hole? How can a black hole be that large? What even is a black hole? What about the long lines of filaments that we see in the universe? Structures. Could there be a biological structure to the universe? Well, it turns out there is a statistical correlation between the structure of the universe and the neural networks of brains. In 2020, researchers at the Istituto di Radioastronomia in Bologna worked with the Department of Neurosciences at the University of Verona. And they created this research report in Frontiers in Physics, dated 16 November 2020, the quantitative comparison between the neuronal network and the cosmic web. So quantitative comparison, statistical analysis comparison between neuronal network of brains and the cosmic web network. The authors say we investigate the similarities between 2 of the most challenging and complex systems in nature, the network of neuronal cells in the human brain and the cosmic network of galaxies. Look at that. So they compared neurons with galaxies. So they sliced brain matter of rats, actually it's super thin, and they looked at each neuron as a point. Similarly, they took the actual mapping of the universe, the dark matter mapping, and they took each galaxy as a point and they compared those using statistical analysis. It's pretty interesting. So the paper actually compared the structure of tiny slices of cerebellum and cortex to the design of dark matter distribution of the cosmic web. Some exciting points they found are water and dark matter make up around 75% of the medium. In summary, the brain is composed by water, 77 to 78%. Lipids, 10 to 12%, proteins, 8%, carbohydrates, 1%, soluble organic substances, 2%, and salt, 1%. Your brain is made of 1% salt. That's what you're worth in salt. The universe is made up of 73% dark matter, a scalar energy field of empty space. It's just empty, right? Just empty space out there, scalar energy field. 22.5% by dark matter. Again, we don't know what that is. And 4.4% by ordinary baryonic matter. That's you and me. That's everything we can touch and see. That's baryonic matter. Only makes up 4.4% now. And less than 0.1% by photons and neutrinos. So this is light and neutrinos, things we don't really understand, I think. We put it as less than 0.1%. So strikingly, in both cases, 75% approximately of the mass energy distribution is made of an apparently passive material that permeates both systems and has an only indirect role in their internal structure. Water in the case of the brain, and dark energy in cosmology, which to a large extent does not affect the internal dynamics of cosmic structures. So it's almost like we're under the ocean, like fish, and we're looking out there and we can't see the water. We just assume there's something there. It's dark matter. There's got to be something there, but we can't see it. It's this invisible structure. Also works like water. So I thought that was quite interesting. When the researchers compared the density of nodes, a neuron is a node in the brain, while a galaxy is a node in the universe, they found that the thickness of neurons in the cerebellum matched the patterns of dark matter in the cosmos. The similarities don't stop there. When the researchers compared the density of nodes, a neuron is a node in the brain, while a galaxy is a node in the universe, they found that the thickness of neurons in the cerebellum matched the patterns of dark matter in the cosmos. So this is cerebellum at 4 times zoom, cortex at 4 times zoom, and then the cosmic web zoomed at 4 times. These are millimeters, and this is megaparsecs, 10 megaparsecs. So here's the cerebellum, and now we go to 10x. So at 10x, you can start to see some structures little forming here in the cortex as well as the cosmic web. You see, these are these structures. Looks like some sort of neuronal network. right, to me. And then we go to 40 times zoom. So you have cerebellum at 40 times. You see these filaments, okay? You see these structures here, organization. The cortex looks quite similar to cosmic web to me, actually, and then the cosmic web here. The authors say the similarity between the cerebellum on 0.01 to 1.6 millimeter scales and the dark matter distribution of the cosmic web on 1 to 102 megaparsec scales is remarkable. They're saying similarity is remarkable between the cerebellum and the universe on different scales. The authors also noted the density of other natural systems, such as sky clouds, tree branches, or MHD turbulence and water turbulence, did not match the dark matter distribution. Okay, so basically here's what you have, the cosmic web, dark matter. This is the distribution. Okay, and baryons actually falls off here, and there's cerebellum and cortex. So if they actually look at the cerebellum and cortex, it follows the same distribution actually. So they looked at actual distribution, how spread out is it? And what they found is statistically, it matched. The cosmic web with dark matter matched the cerebellum and cortex the best. Meanwhile, these other natural systems, sky clouds, tree branches, MHD turbulence, and water turbulence, didn't match. The study's final results hint at the fact that similar network configurations can emerge from the interaction of entirely different physical processes, resulting in similar levels of complexity and self-organization, despite the dramatic disparity in spatial scales of these two systems. So imagine that you have two systems that have the same result, the end result of their structure, but they're in vastly different size scales. And they came into being through different physical processes. That's what they're saying here. Our results hint at the fact that similar network configurations can emerge from entirely different processes. So that means the same neural network, the same or similar network configurations can emerge at the galactic level, at our level, and maybe even smaller at the minuscule microscopic level. Different processes. So maybe at the small level, the way it gets there is different. How the physical processes are made, the dimension of that level, those laws, but the end result, the neural network that forms is the same. Imagine that is the same, despite huge differences in scale. This is their final study results. Within the range of simplifying assumptions we used to define both networks, okay, how they did it, they had to simplify it. Our findings hint at the fact that similar network configurations can emerge from the interaction of entirely different physical processes, resulting in similar levels of complexity and self-organization, despite the dramatic disparity in spatial scales, 10 to the 27 of these two systems. So imagine that. What they're saying is a similar network configuration, so a similar neuronal network can emerge at vastly different size scales. So at the galactic level, we can have a neuronal network forming using different processes, entirely different physical processes, black holes and galaxies. Meanwhile, down at the microscopic level, we can also have neuronal networks emerging inside our brains based on different biological processes. The idea is both would be biological, both would somehow be related to life. Zooming out of this image right now is actually not a James Webb Space Telescope or space image. This is an image of a microfluidic device of neurons, right? This image, this is 1 second actually in the annual Nikon Small World Competition, the 2021 photomicrography competition. And right here, look at this. This is a microfluidic device containing 300,000 networking neurons in 2 isolated populations. Okay, so these are synthetically made neurons, 2 isolated populations. Both sides were treated with a unique virus and bridged by axons. I don't even know how you do that. This is from the Dementia Research Center out of Australia. Amazing. But what you see here is, it looks like the galaxies, man. It looks like those images from James Webb in the deep field. These are neuronal networks, and this is at the microscopic level. This competition is amazing. There's one other image in here, is this one. But this is the rear leg, claw, and respiratory trachea of a louse. If we look back, the Carina Nebula, imagine you're on one little cell in here and you look out. What do you think you would see? Would you see like the Carina Nebula? So what if we're just one dimensional level of a universe unimaginably vast in size dimensions, Although Galileo used lens technology 400 years ago to confirm we're not the center of the universe, not much else in our theories have changed. Could it be that when we look at the JWST images, we get that same glimpse into a world unimaginable to us just a few years ago? When we finally had the technology to peer into the microscopic world, we were surprised that life permeated everything, every environment. Not only that, it was ubiquitous everywhere we looked. Why would it be different when looking at the macroscopic world? As we look up at galaxies, could it be that we're actually seeing the same thing? It's just us limiting us. It's our paradigm shift, our own paradigm limits. Because everything stops at the human level, right? There's no life above us. Oh, there is life below us because it's been proven. What do you think, James Webb Space Telescope? Do you think it'll highlight our role in the universe? Do you think it'll change humanity's paradigm? What's the coolest thing you saw in the images so far? What's your favorite thing in the James Webb Space Telescope images? Let us know in the comments. Smash that like button if you did like this video. Subscribe to get future content, notifications of my videos. I release a video at least every Friday. And then support the channel on patreon.com/Chris Lato. Access to live streams, behind the scenes, information, and events. Should be exciting. And you'll notice on my channel, I never give ads for any VPNs or other software online you can pay for, okay? We're just focused on unidentified aerial phenomena. And that's why we created the society, the UAP Society. So if you do want to get involved, you want to get your hands dirty, you're tired of not being told the information, we want to find the information on our own, and we're serious about it. So thanks for being here. You can find all the links in the description, and we'll see you next week. Peace.